Alright, this is our last section of Chapter 7 that we're going to look at, and this section is about moments, centers of mass, and centroids. So the first thing we need to talk about, and this is a chemistry kind of thing many of you have seen in chemistry, is the idea of what mass is. Mass is actually a measure of a body's resistance to change in motion. It is independent of the gravitation system you're in. Sometimes we kind of think of it as being equivalent to weight. That's not really technically correct. Weight's a type of force, and it's related as force is mass times acceleration. So the acceleration the gravity's pull on us creates this force, which is our weight. There's several different commonly used measures for mass and force if you take a look on page 498. And we're going to take a look at the center of mass in three different situations. The first is the center of mass in one dimension. So the moment of mass is the object's ability to resist rotational change. It depends on both how heavy, or the mass, of the object, and its distance from where the object is being moved. And that distance is from sort of a point we're going to call a fulcrum. So what you want to have in your mind is a teeter-totter. So if you've been on a teeter-totter recently with a child, the issue, of course, is that if your weight and the weight of the person opposite you on the teeter-totter are not equal, then one person ends up stuck up in the air. And so we can sort of counteract that in a couple of different ways. One way we could counteract that, and physically what we do on the playground, is the heavier person has to move closer towards the center of the teeter-totter, and at some point they're close enough toward the center that there's a good balance going on and we can teeter-totter just fine. Well, what we're going to be doing here, instead of moving the persons on the teeter-totter, is we're going to kind of move where the teeter-totter is hinged, and that's our center of mass that we're talking about. So we're taking a look at our first example. We're going to consider a person weighing 200 pounds. They're sitting on the end of a 5-foot-long beam, and they've got a 600-pound rock that they need to lift. And we're going to figure out where we would need to place the fulcrum, that centered location, in order for that to be able to happen. So here's my beam, my teeter-totter, and we have this teeter-totter, and it's 5 feet long. We have our person on one edge, and they weigh 200 pounds. Again, we're relating this with weight, and which is not technically correct, but it will still hold true. And then we have our rock on the other edge, and our rock is 600 pounds. And at some point in here, we're going to put a fulcrum, and I'll draw it in red. And this red piece right here is a certain distance away from the person, and it's a certain distance away from our rock. So we're going to call the distance that it is away from our person x, which means that the distance away it is from the rock is 5 minus x, because my full distance is 5 feet for this beam. And what we want is we want these two actually to be equal to one another. So we want to be able to take our moments, which is our mass, so this is the 200 pounds, times x, the distance from the fulcrum, so 200x, to be equal to the mass of the second object, which is 600 pounds, times its distance from the fulcrum, which is 5 minus x. And we end up with a simple linear equation that we can solve. So I have 200x equals 3,000 minus 600x. I can add my 600x to both sides, giving me 800x on the left, and I have 3,000 on the right. And then if I divide by 800, then I end up with x is equal to 3.75 feet. So my picture is very misleading because it looks like my fulcrum is closer to my person, and it's actually closer to my rock. So the distance from the person to the rock, no, I'm sorry, not to the rock, but to the fulcrum, person to the fulcrum, is 3.75 feet. And likewise, we could find the distance from the rock back to the fulcrum as well, and that would be 5 minus the 3.75, or 1.25 feet. All right, so we can generalize this idea to having multiple people on the balance beam, or multiple people on our teeter-totter. And so if we had n different people, then they would each have their own mass, m1 through mn. They would each have their own distance from the fulcrum, x1 to xn, and if we added those distances times the masses together, we get this summation that you see on the right-hand side. And the point where we get this moment to be 0 would be an equilibrium point. And for a system that's not an equilibrium, this would be the center of mass. It's a point where we would place our fulcrum so that we would be in equilibrium. And this x bar, this center of mass location, is the moment divided by the total mass. So we're going to take an example of this, and my values got erased, so let me write these in here. I have mass 1 is 12, mass 2 is 1, mass 3 is 6, mass 4 is 3, and mass 5 is 11. And then I have distances. My x1 distance is -6. My x2 distance is -4. My x3 distance is -2. My x4 distance is 0. And my x5 distance is 8. And our summation then, from I equal 1 to 5 of m sub I x sub I would be simply each mass times its distance. So I'd have 12 times -6 plus 1 times -4 plus 6 times -2 plus 3 times 0 plus 11 times 8. And if you add these up and multiply and add these up, you'll end up getting that this is actually equal to 0. And we'd also like to find the summation, because in general it won't be 0, from I equals 1 to 5 of simply the masses, that is the total mass. So that's just a matter of adding up the 12 plus 1 plus 6 plus 3 plus 11, which gives us a total mass of 33. And then in general we would find x bar by taking the first summation, which was 0, divided by my second summation, which is 33, and we would have 0. So what that actually means is that the center of mass is the origin. So if I were measuring these distance away from the origin so that I got the -6, the -4, and so forth, my origin would actually be the place where I could locate my fulcrum and have the values balance. Now, where we're moving in our next class is to take a look at doing this on a two-dimensional shape. So some example of like blocks on a plate. So if we had a plate and we put different blocks on it, we would still want to be figuring out where we could place a point and balance our plate on that. So we're going to take a look at an example of that next time.